First thing we're going to talk about is linearity. What's the key word in linearity?
Linear.
Linear. So we're talking about lines. So what we need to be able to determine linearity is whether or not a function is a linear function. Well, you've done a lot with linear functions. Tell me how you recognize, algebraically, not graphically, how do you recognize a function being linear? Algebraically, though. It's what? Has a what? I didn't hear you.
X and Y.
No power, X and Y. So I'm thinking it could be written this way. Linearity. Linear with an ITY on the end. It could be written this way. We've also done standard. And we did point slope. But the point in all of these that you notice is no matter what form you're in, you're right. X has no exponent on it, right? So I'm looking. That's right. You can say right. Right, Miss McGee, that's right, guys.
Right. Correct.
No exponents on X. It's just an X, right? You got to have an X in there. So if you see this happening and there are no other exponents, now I could put an exponent on one of the numbers. In other words, I could have 2x plus 3 squared. Is that linear?
Yes.
Yes, it's the x that I can't have an exponent on, okay? Not on the y either. Not on the y either. Not on the y or the x, okay? If it's an exponent on y, it depends on what it is. It ends up being, it depends on what the exponent is, but it ends up being a type of radical function.
You have to like solve for y.
We will get to those, like a square root or cube root or fourth root. Okay. All right. Shh. I want you to look at these and tell me yes or no. Is this a linear function and why?
Yes.
Why?
There's no
exponent.
No exponent on the x or the y. It can be written in slope-intercept form. It's already in what form? Standard form. So yes, this is a linear function. This is easy, right? How about this one? Ooh. Sure? What happens if it's in the bottom? Do y'all remember properties of exponents?
Do you have to put of one like over something?
All right, so
On the x?
1 over x is the same thing, x to the negative 1. Do you have an exponent on x of anything other than 1?
Yeah.
So is this a function? Is this a linear function? No, this one is a non-linear.
So would it be like
What?
All right,
over x to the negative squared?
it's got to be a positive 1. If it's anything other than 1 on x, it is not a linear function.
So how would you solve that?
Well, we're not worried about solving it. We're just worried about what it would look like. Look at what...
Would it end up with?
Let me show you. I don't look at that yet. That's a surprise. 1 over x graph. Ooh, is that a linear function? Does that look like a line graphed on there? No. It is not linear, okay? All right, listen, guys, I need y'all with me, okay? It's not a linear function, so graphically I can tell it's non-linear. And then algebraically, because there's an exponent other than 1 here, it is not. Y'all with me?
Wait, if it was just one, would that be? If you were trying to get the x out of the fraction, would it be x negative?
If you were trying to get, you could multiply both sides by x and you would get 2 equals x times y. But again, when you solve that for y, if you've got 2 variables that are going to multiply together in your equation this way, it's not going to be linear. Because whenever you would go to solve it, you'd end up with an exponent other than 1 on x. So even though that looks like it could be linear right there, you would need to solve it for y, and when you do, you would see that you'd end up with something other than 1 on x.
So are we always going to do the able to graph it to figure it out?
You can only graph when it's solved for y. But if you want to solve it for y, you could, yes.
If it's like x with like the
That's a good question. So if I had y equals 1 over x to the negative 1 plus 2, is that a linear equation? Yes, it is a linear equation. Think about two negatives make a positive, right? If it's negative in the bottom, you move it up and make it positive. It changes the sign when you cross over the fraction line.
So n would be x.
So this is the same thing as y equals x plus 2. So yes, that is linear. All right, so we're looking for exponents other than 1, and we're looking for, if it's not solved, that's if it's solved for y. If it's not solved for y, we're looking things like variables being multiplied together and showing things like that. Yeah. What? It's a cubic. It's a cubic. All right. How about this one? Linear or nonlinear? Nonlinear, why? Those x and y's are multiplied together. Again, if I had to solve it just for y, I'm going to end up with some crazy exponents, right? Just like I did before on the one before. And you don't have to solve any of these. You just have to tell linear or nonlinear. How about linear? It is linear. If you can ever get it back in the form, mx plus b, it is linear. Okay? One more.
Why do they do all those variables? Is it just 30 long? Why are there so many f of x, g of x?
Just so you can determine that the purpose of function notation is so that you can reference different functions and you can say, okay, comparing f to g, what happens from here to here, instead of, so it's not like, look at, if they were both y equals, it's kind of like naming them. Okay. Like you're Noah and you're Connor, so that I can decipher between the two of you. We name the functions so we can decipher between the two of them. Is it? It is or it isn't? Is it linear? I hear no. Defend your answer. It's in the denominator. If you see x in the denominator, that's automatically going to be some type of negative exponent somewhere. So it's nonlinear. Nonlinear. I guess I should write these on here. Linear.
Because x is in the denominator?
Exactly. Are we all okay on determining linear versus nonlinear?
I think so.
For now. For now. Okay. Let me read you a problem. Ready? I'm gonna call her Mal. Mal and Helena work part-time at a smoothie store because that's where every teenager works, right? The number of hours they worked increased the first 5 weeks on the job. The graph models Mal's weekly earnings and the table models Helena's weekly earnings for these 5. We want to know if each relation is linear or not. So Mal's is going to look something like this. And Helena's is going to look something like this. Y'all always say that word problems kill you, so. This, I'm going to put money, that just means how much she made. 1, 2, 3, 4, 5. 60, 120, 180, 210, 240. All right, so my question is, this is Mal's. This is Helena's. Look at the first one. The first one's in the form of a graph, the second one in the form of a table, but both of them could be represented graphically. Does the first one look linear to you?
Yeah.
Why? Because it clearly looks like a line with a constant slope, right? Of course, I mean, it was supposed to be. My one dot's a little off, but that's okay.
Does that have
Huh?
yeah.
Yeah. If it didn't, if one of these points was up here, like if this one wasn't here, it was like that, that would be non-linear.
Is that going into the point of best something? Where you
Line of best fit. We won't get into that a whole lot, but it could be, yeah. All right, how about the table? Here you gotta think a little. Ooh, why?
Because it goes from 18 to 21.
Okay, so non-linear. So give that to me in terms of mathematical language.
So it goes 6.
All right, you're saying it's increasing 60.
Yeah, and then increasing 6 again. And then increasing 30. And then.
So the change in money is not constant. What does that tell me?
The slope of what will possibly be on.
There you go. Good job, Dan. The slope is not constant. If the slope is not the same between all the points, it is not linear because a line must have a slope, and it must be the same between all points.
Can they change your pay? Just like that?
I suppose.
It's probably just on 10.
Or maybe they said for every week you come in that you're here on time every week, and then we'll stop it at this point. But yeah, maybe so. Yeah, because it doesn't say hours. Maybe they gave them more hours each week. All right. Everybody good on linear versus nonlinear? Okay, I feel like I'm running it in the ground. All right, let's talk about symmetry. This is fun. Come on now. We have two types of symmetry we're going to talk about. The first is linear symmetry. Linear symmetry. Tell me what you think that might mean. It has a line of symmetry. It is symmetric about a line. So rewind back to geometry. Okay? If you cut it in half by a line, it's the same on either side. It mirrors each other, right? It's reflected. It's got a line of reflection. It's cut in the middle. What is one that you have done that would be symmetric about a line? Well, something graphed. So a line like this is symmetric about what line? What would the line of symmetry look like there?
The perpendicular line.
Good job.
Yeah.
Good job, man. That's the way, not perpendicular, but you get the point. The line perpendicular to that would reflect it over. It would be symmetric about that line. What's something else we've done that you didn't probably know until we started doing it, but we started graphing it a little bit?
Parabola.
Yes.
So it's linear symmetry, you can put a line through it.
If it has a line of symmetry, yes.
It's symmetric over the
It's symmetric
Yeah, over the y-axis.
about a line. But you're right, straight down the middle. If you can cut it in half and it's the same on both sides, then yes, it has line symmetry, yeah.
What line wouldn't be symmetric? Because like every line I think would have like a...
Lines, yes. All lines are going to be symmetric about some other line. But we're going to talk about a lot of different functions. And I'm going to give you some different graphs that look different. You might not know what they are, but just to say, does it have linear symmetry, yes or no?
Because I think like every line would have like a...
It would, you're right.
Wait, how is it always solved?
We're just, right now, what we're doing in this chapter is we are doing some analysis of functions. And so we're going to talk about lots of different characteristics and things that functions have. This is just one of them. Functions could have linear symmetry, or we're going to talk about the other symmetry in just a minute.
Wait, if the reflection of both of those lines have the same slope, why would parallel lines be?
Well, we're not talking about two lines, we're just talking about one line. Like you're trying to add something else there. I'm just talking about one function at a time. Parallel lines would be two different functions because they'd be two different lines.
And so if you just look at a line, how would you really tell?
All lines have linear symmetry.
Then how is this?
about the middle.
Yes. Okay, so
You're just looking at it. It's a visual thing. You're looking at it. Could you fold it in half somewhere and it look the same on both sides? Then it's linear symmetry. Okay, does that make sense? I think y'all are way, way, way overthinking this.
So,
Um,
so how if that line, that second line is going like one like this?
That's what I was fixing to show you. All right, so that's a cubic. This is actually what we call a quartic. This is the graph. It looks something like x to the fourth. Okay, you don't have to know that yet. We'll get to it. You don't have to know that, but just go back. Is there somebody say go back? Katie asked earlier what this is. This is a cubic. Again, you don't necessarily have to know that at this point. But does this have linear symmetry?
No.
There is no way if you put that on a piece of paper that you could fold it just one time some way and it be the same. But it does have something special. Okay, say it again, Noah.
Does it reflect and rotate?
It rotates. Yes, it rotates. Good job. So what it does, this is what we call point symmetry, which means it rotates around a certain point. Sometimes this is called rotational symmetry. Okay. It means that it's symmetric about a point. If you rotate it 180 degrees about some point, any point, I mean different ones are going to have different points, then it maps back onto itself. You remember?
Yeah.
That's called point symmetry. Now let me show you. This is so cool. Y'all ready? Look. Rotational symmetry or point symmetry. This is symmetric about the point 0, 0, 0, 0 is the point that if you rotate it 180 degrees, it maps back onto itself.
What about in this 1, 1?
But 1, 1 is
1, 1, it would not.
it's on
If you rotated about 1, 1, it wouldn't be on it.
So if you put it on any point on that line,
It has to be the point 0, 0. If I tried to rotate about the point, let's say 1 negative whatever this is. If I rotated it from there, it wouldn't match up onto itself. It's rotated about 0. Yeah.
1, 5, 5. 1, negative 1. We did this
Well, you're still yes, but you're still rotating about 0, 0.
no, why right some point then?
All right, look. Because you have to determine the point that it's rotating about.
So like other things could not even be drawn on 0, 0. I see what you're saying.
Reflectional, that's when I have a line of symmetry or a line of reflection. So you see how this is reflecting over you.
Could you take any point on that and like reflect it and then do something else to make it, instead of rotating it, you reflect it and do something?
You're still going to have to rotate it.
Okay.
Yeah, you're still going to have to rotate. Now, about the origin, that's really a reflection over X and then a reflection over Y, right? Am I remembering right with geometry?
What was the question?
When you rotate a point in geometry, if you rotate about the origin, is that a reflection over X and then Y,
It is.
or is that
If
you what?
If you go 180.
180? Yeah, and that's what we're going is 180. But that's only when it's 0, 0, when it's reflected about the origin.
I was saying like
All right, so look, there's your linear, right?
Does it have to be over an
No. Look at this one. What type of symmetry do you think this function has? Ooh. Maybe we should save this for tomorrow.
Either.
We might save this for tomorrow.
like wouldn't it be like
Who says reflectional? Raise your hand. Who says rotational? Raise your hand. Who says neither? Raise your hand. Ooh.
Wait a second.
Wait, it's rotation.
Wait, neither.
Flip it.
No, because if you flip it, they'll be like that.
It's both. It's like reflected over something.
Neither.
Yeah, no,
It's neither.
yeah, if you rotate it at 0, 0, I think
Yeah, it's not
Neither is neither.
It's rotational. That's in it.
It's rotational.
Yeah. Rotate about 0, 0.
I was hoping it would have a little. If you went 180 degrees, just like this one does, see how that one does 180 degrees? If you went 180 degrees with this one, it would map back onto itself.
Yeah, but I did like the top one has to go into the
If you went about 0, 0.
If you went about the origin, you see it? Okay. All right.